Hello, my name is Sayad. I'm an assistant professor at the University of Tehran, and today I'm going to talk about the security of cyber-physical systems, and more specifically covert attacks and how we can detect and compensate them. Here is the agenda for the talk. We start with the definition of cyber-physical systems, and more specifically network control systems. Then I'm going to give you the adversarial model that we are going to work with, and then I give you 3 examples on how covert attacks can be launched on physical systems like the DC motor and then intelligent transportation systems. A control loop is composed of a controller and a plant, and usually 2 links that connect these two to each other. In network control systems, a branch of the cyber-physical systems that we want to deal with, these links are actually network links. An attack can happen in any of these places. So it can happen in the forward link, it can happen in the backward link or feedback link, it can happen on the plant as a physical attack, or it can be in the controller, which we haven't shown here, but that can also be a place of attack. Okay, for the time being, let's assume that it has happened in the forward link, and we know it is there. Okay, I'm not going to talk about that. We have a model to detect the place of attack, but for the time being, for the sake of simplicity, assume that it is in the forward link and we know where it is. Here's the abstract model for the same loop. Just assume that we are sitting here and we are the good guy. We are, by sitting here, I mean the IDS is next to the controller and the plant is not faulty. Okay, we have heaps of models to detect faults in control systems. That is the expertise of control guys. I'm not gonna look into it. But in our model, the plant is not faulty. So anything that goes wrong is a result of attack. The 2 network links are protected by keys, meaning that the integrity is protected, or we can even protect the confidentiality. So the sensor reading is, for example, encrypted and protected, and goes to the controller, and the controller sends the control signal in a protected way to the plant. The attacker in our adversarial model is allowed to compromise one of these keys, one of these 2 links. Why not both? Because if an attacker is so powerful to take control of both these 2 links, then it can virtually detach controller from the plant and pretend to be a decent and benign plant to the controller and a benign controller to the plant. And there is no way we can detect something is wrong. In the first example, and to introduce the concept of covert attacks, I take a DC motor as a plant. Well, just imagine I set a reference speed. I want to increase the speed of the motor from 0 to that reference speed. A normal controller increases the speed, possibly after an overshoot or undershoot. The motor speed settles at R. In covert attacks, we want to change the system output in a way that is not noticeable to human observers, but damages the system in the long run. For example, if in the forward link, at some point of time, I decide to multiply the control signal by k, as k is greater than 1, intuitively it increases the output speed. It creates an overshoot in the system. But because it's not too big, let's assume it's not too big, the controller manages to bring the error down to 0 and then speed back to the nominal one, I mean the reference speed R. If the transition is small enough, a human observer cannot notice the difference. But if it happens repeatedly over the time, because that is above the nominal speed of the motor, it can damage the DC motor and reduce its lifespan. Okay. In another one, just assume that the system is linear for the sake of simplicity. If I insert a transfer function here in order to create a steady state error, yes, again, maybe a few percent increase in the speed doesn't draw the attention of a human observer, but that error, because it's permanent and the DC motor is working above its nominal speed, then again it can reduce the lifetime of the DC motor. Okay, so these are the covert attacks, two types of covert attacks that I wanted to show you on a DC motor. Now let's get back to the idea of detecting and compensating the attacks, the covert attacks. In this case, if I imagine or assume that the system was initially uninfected and uncompromised, then I have a safe period during which I can learn the behavior of the system. In this case, I can learn the behavior of the plant and make a model out of that. Or if equivalently, I can use the model of the plant if I have the mathematical equation for it. Then, whenever the controller sends the control signal, I can use the same in my local model, in the IDS. And if the output that comes out of the plant is significantly different from my expectation, I raise a flag, I say the system has been intruded, and for the compensation, yeah, I can prescribe something. In this case, I switch the controller. I bring in a backup controller. Remember that in covert attacks, the attacker has learned both the controller and the plant and has tuned the parameters, the attack parameters, in a way that the output, the effective attack, remains in the unnoticeable range. Okay? So to compensate, we used a model-free controller, hoping that since the attacker hasn't learned the backup controller, it was never in the loop, it can manage to bring the attack effects, side effects down. This is the complete picture of the control loop and the intrusion detection system. As you can see, the DC motor, here is the plant. There is, this is a controller, but we have two of them. The default one is a sliding mode control, augmented with neural network controller, and the IDS uses a plant model which was trained during the initial period of system operation. And whenever the IDS sees a significant deviation between the system output and the plant output, it switches the controller, and the PID controller, which is a backup one, kicks in. The network links are CAN bus. As you know, it's a standard for in-car communications, but it's not protected at all. I mean, not most of the times. So they can be easily compromised. These are the results for the first attack scenario, in which the attacker tries to create an overshoot. In the left one, the attacker strength was 15. If there was no detection and compensation system in place, the attacker could increase the overshoot as much as 50%. In the second one, it was even more severe, with a high gain of 120. The system would become unstable, but this is not a covert attack. Okay. In both cases, we can see that almost immediately, after a few milliseconds or a few hundred milliseconds, we could detect the attack. And if we kicked in a compensating PID controller, which the attacker hasn't learned, we could bring the overshoot down to 17% here, and here make the system stable. Okay, But what if, we told you what happens if the forward link is compromised and how we can detect and compensate it. Gave you an example. But what happens if the controller is compromised? That was the case with Stuxnet. It's the same idea, okay? I told you I want to give you a general idea how to detect covert attacks and possibly compensate them in cyber-physical systems. The idea is to monitor the behavior of the suspected component and see if it behaves as it is expected. In this case, I monitored the behavior of the controller. We took the adaptive car cruise control for this example. Modern cars have radar. They try to sense the front car, the lead car, as the terminology says. If the distance to the lead car is more than a threshold, they follow the cruise speed. If you set it at 80 miles per hour, it goes at 80 miles per hour until it gets close to the lead vehicle, and then reduces the speed so that it maintains a safe distance. And safe distance is defined based on the speed itself. So at higher speeds, the safe distance is more. So you have to keep a safe distance, a safe relative distance, so that if the lead vehicle suddenly brakes, you can react. Again, we have the same control loop, okay? We have the cruise controller, which controls the acceleration, and then we have the car dynamics is the plant, and we have the same bus in the car that carries the feedback signal and the control signal. We define two types of covert attacks here. One, okay, the attacker waits till the two cars get close, and then instead of decreasing the car speed, just doesn't do that. I mean, lets the car go at the previous speed, so that temporarily the distance between the two cars gets lower than the safe distance. Okay, this might not lead to an accident, but statistically over the long run, if something happens to the lead car, then we don't have enough time to react. In the second one, the adversary manages to permanently reduce the reference for the controller and bring the distance between the two cars lower than the safe distance. So it changes the definition of safe distance. If it is a 50-meter distance, it makes it 40. This is not a science fiction movie we are talking about. This is reality. In 2015, these two guys showed how a Jeep Cherokee can be hacked, and they took control of everything: steering wheel, brakes, engine, central lock system, wiper, air conditioning, everything remotely via the internet and through the car entertainment system. If you have time, just go and watch this video. It's like a 5-minute video. It's worth watching. Let's get back to the detection and compensation model. As I told you, we monitor the behavior of the controller. In this scenario that we have designed, which is a paper we just published, we use the model predictive control or model predictive controller as the main system controller. We use a neural network identifier that learns how the MPC controller works in the initial safe period. Well, if you have worked with MATLAB toolboxes, the Intelligent Transportation System toolbox, you might have seen the example that a deep neural network tries to mimic the behavior of an MPC controller. I think you can find the source code online. But anyway, a neural network tries to learn the MPC controller and mimic the outputs of the controller. So whenever there is a sensor reading, it is fed to both of them, and if there is a significant difference between the MPC controller output and the neural network output, a flag is raised. So the detection has been done. But what do we do for the compensation? Again, Since we know the controller is not doing its job well, we replace the controller upon detection of the intrusion with a simple backup controller. So to keep it simple and cheap, we use the P controller out of a PID. And here you can see the result. Almost immediately, like after a few hundred milliseconds, I think it was 200 or 300 milliseconds, after the attack, we managed to detect the misbehavior of the controller. And then we kicked in the substitute controller. Okay, this is the first attack, the first covert attack, in which the attacker tries to temporarily bring the distance of the two cars lower than the safe threshold. As you can see here, without intrusion detection and compensation, it achieves its goal. But with the intrusion detection and compensation, a strategy that we just told you, we keep the safe distance permanently. Again, in the second attack scenario, the attacker changes the reference for the safe distance and manages to bring the solid line, which is the actual distance between the two cars, below the safe distance, which is the dashed line here. With the attack detection and compensation model that we prescribed, we can maintain the safe distance. Okay, we told you about the attack in the forward link, we told you about the attack in the controller, and what if the controller is safe, the forward link is safe, but the feedback link is compromised. So here has been attacked. What does it mean? It means that the sensor readings cannot be trusted. There are multiple sensors in new cars or autonomous cars. There are stereo cameras, radars, GPS, and many other things, okay? All of them are used by the controller to, for example, control the steering wheel and the acceleration. Just imagine in the future cars, the autonomous cars, malicious worm spreads in the vehicular system or intelligent transportation system that sits in the feedback link, manipulates the sensor data and lies to the controllers so that some sort of desired output is created for the attacker. We just don't tell you yet, but as an example, in our latest research, we tried to lie to the controller about the car position in the lane. You know that new cars can drive between the lanes automatically. They have stereo cameras. They see the lanes. They try to stay between the lanes and drive automatically without any help from the driver. Well, here is a video that we have made by simulations. We lied to the controller about the car position with respect to the lanes. So we told the car it was not actually at the center of the lane, but it was like a few meters away from that. And as a result, the controller tried to fix that, which in reality meant it got close to the lane boundaries, and that could possibly lead to a crash statistically, not instantly. So on the left we have the normal scenario, at the center we have the attack scenario, and on the right you can see where the car is on the map. As you can see at the middle, when the car approaches the corners, it dangerously gets close to the lane boundaries. Of course, this is a simulation, but it gives you the idea how the attack works. To detect such attacks, we have to rely on inconsistencies between sensor readings. As I told you, the car has multiple sensors. If an attacker is powerful enough to fake every signal in a harmonic way, I mean every reading rhymes with the other readings, we have no chance of detecting anything. It's as if I give you a virtual reality headset and show you the fake world, in which everything is right. Okay, well, it is not. I mean, you're jumping off the cliff. You're at the verge of jumping off the cliff, but I say no, there is nothing wrong, and you can go ahead. The only chance is that there is some sort of inconsistency between readings. Okay, and here we assumed that the attacker has lied, changed or manipulated the lane sensor readings and told the controller you're off the central part of the road by, I don't know, 2 meters, but the GPS readings have not been compromised. So we know where we are. With that information and with the lane readings, I can reconstruct the road. And if I have an offline version of the map, like a Google map that has been stored on a flash memory or something, which doesn't take too much of a space, I can compare the reconstructed road with what I have in Google Map, for example. If you look at the right, in this specific circuit, I've shown T6 and T7, which are the two turns, and the gray lines show the reconstructed map, the reconstructed road, and the dark ones show the original that came out of the map. Okay, and you can see there is a difference. From this, I can detect something is wrong, and possibly the readings are not consistent or the integrity has been compromised. Then I raise an alarm, and the driver is asked to take the control back. What we have learned in this talk is that, yes, covert attacks can happen. They can be in the forward link, in the feedback link, in the controller. It can be even in the plant, but we have heaps of solutions for fault detection on physical entities. So we leave it to the control guys. With the others, we should develop component-based IDSs to monitor the behavior of those components, see if they behave as they are expected. We have formal methods to check the behavior of a system, and they work perfectly well. But the problem is that with formal methods, when the system size increases, the model gets exponentially complex. It is perfect, but it's not practical for big systems. With this, we have a less perfect system, we have a less perfect solution, we leave detection to the small components or small IDSs that were designed for each component individually, and if anything goes wrong, that component IDS will let us know, raise an alarm. It can be a watchdog or something that has been embedded into the system during the construction of that component and kicks in whenever, or raises an alarm whenever something goes wrong. I hope you have enjoyed this talk. If you have any question, you can contact me via email, which is written here, and I hope to see you in the next conference.